So our goal in recording today's symposium is to have a chance to share the work that was done by these students with others as we go forward, and also to have them have a chance to take and actually see their presentations later on and see how much work they have done over the last year. As we're getting started, I just want to start off by welcoming our guests. I know that today we have both the students, we have other faculty members and students from across campus at Central Washington University, and we also have friends and family that are joining us here today to hear about your students. And so I want to take a moment and talk about what a summer REU experience is. So these students just did a research experience in undergraduates. And formally, the Council on Undergraduate Research defines undergraduate research as an inquiry or an investigation conducted by an undergraduate student that makes an original intellectual or creative contribution to the discipline. And so that's what our students are going to be talking with you about today, is their process in doing that. When they first got here 8 weeks ago, we gave them this whole entire list. This is all the things that we thought that they might be doing this summer. But then we asked them last week what their experience actually is. We asked them to tell us in one word what it was like to do research. And you'll see that the students have had a combination of experiences, everything from it was awesome to also just feelings of chasing your tail or feeling directionless, feeling like you've done something really complex and that you've conquered it, while also feeling relief as you're able to clarify, as you have breakthroughs, as you have a chance to take and get past those frustrating feelings to feeling like you have gotten some awesome results. And so we are really excited for our students to be able to present their work today. We're going to have 3 sets of presentations. Each presentation will be 15 minutes long with 5 minutes afterwards. We're going to ask that you not interrupt any of the speakers as they are presenting and that you save any of your questions for the end. If you're not sure that you'll hold on to that question, you can always type it in the chat and the students will be able to respond to it at the end of their presentation. You'll see each one of our groups is made up of 4 sets of students. These students come from across the country, and they were all able to join us this year virtually, just as you are joining us here today. And so we're really excited to have this broad range of backgrounds joining us and being able to move forward on these topics. Our very first presentation, which will start in 1 minute, is going to be about a topic of utility theory. The advisor is Dr. Loke, who did our introduction today, and Ashley, Austin, Dylan, and Michael will be doing the presentations. And then at the end, we'll have a chance to say thank you to all of them. I guess before we go off, I do want to also just take a moment. I'm sure all of our students would want to say this, to say thank you to all of you for joining us today, because I think these presentations, they've worked so much harder knowing that friends and family are going to take and be joining us. So thank you for being a part of that. So with that, is our first group ready to present? Okay.
Yes.
Take it away.
So I'm Austin.
I'm Dylan.
I'm Ashley.
And I'm Michael.
So today in our presentation, we're going to be going over an introduction into the game show Deal or No Deal, some background on utility theory, a description of the data set that we were working with. We're going to be going over the methods for modeling the banker offer, methods for modeling player decisions, and future directions for this research. So in the game show Deal or No Deal, there are 26 briefcases full of different amounts of money. In the US version, the amounts range from 1 cent to $1 million. The briefcases in the slides are in increasing order, but in the actual show, a third party randomly distributes the briefcases. So neither the contestant nor the banker know which briefcases are which. The contestant chooses a briefcase, and then the rounds begin. At each round, briefcases are opened, revealing which amounts they had, basically narrowing down which briefcase the contestant might have. Then the banker makes an offer to the contestant, which can be seen in the top right corner of the screen. The contestant can either take the offer and give up the briefcase, or keep the briefcase and continue to the next round. The rounds continue, and if by the last round the contestant has not accepted a bank offer, they open their briefcase and get to keep whatever amount is contained within it. So let's click through these next few slides and see an iteration of the game show play out. So the offer here is $279,990.97. Notice that the $1 million briefcase still hasn't been opened. As it gets open, we can see the bank offer decreases significantly. So as we can see, the contestant didn't accept the bank offer until round 9, with only the $750 and $500,000 briefcases left. They end up taking a deal of $202,281.22. If they would have continued on and opened the briefcase, they would have been disappointed to find out that it only contained $750. So we aim to answer a few questions about the show. Given that there's no publicly available framework, how can we accurately model the banker's offer system? What do we know about past players' gameplay? How can we replicate empirical gameplay data and describe it in terms of utility theory? And what methods are best to generate an optimal player strategy?
Moving on to talk a little bit about utility theory. It was first referenced in a paper by Fishburne in 1968. He defined a utility theory as containing a binary preference relation on a set of discrete choices or actions. These relations helps to describe assumptions and theorems about a utility function, and it has certain properties like either transitivity or specific concavity, depending on context. Our project was motivated by expected utility theory, where we seek to identify the optimal decision when we're presented with a choice involving risk. By multiplying probabilities and prize values, we can derive these expected utilities, like in our table below. Empirically, it was determined that expected utility theory isn't the best option to actually describe our game Deal or No Deal. So to move on to talk a little bit about our data, we had two major sources, an empirical set and a simulated set. The empirical set came from that post paper in 2008. It had demographic and gameplay information for 47 players from the United States version of the show. And we developed our simulated data set by deriving demographic data from this empirical data and by using permutations to model the briefcases. In both sets, we stored gameplay data as a Boolean matrix of the binary values of our cases, open or closed. The slide here actually depicts the sample information from the player from the beginning of our presentation. As you can see, we note he is highly educated, stopped in round 9, went home with about $200,000. And here we also denote through the 9 rounds of his gameplay, the expected value and the banker offer that he eventually took. Moving on to develop how we modeled the banker's offer. Since it's not publicly available how the banker makes their offer, we sought to model it. It's not exactly a simple task, so we turned to some machine learning techniques. We used a train test split, which basically involves holding out a percentage of our data to test our model on unseen data. We looked at things like a linear regression, random forest, nearest neighbors, and eventually settled on a deep neural network. Notice that all of the things we tried have an R-squared value of over 0.9, meaning that over 90% of the variability in our banker offer can be described by our input. Here's a little bit of a condensed diagram of our neural network. We feed data through an input layer, through nodes in hidden layers, and through an output layer. For our neural network, we used 108 nodes in each of our 8 hidden layers. A little more about those inputs. We actually inputted round number, case information, previous bank offers, and the expected value of our briefcases. To put the data through and use the weights of these nodes, we used activation functions, 2 in particular. One was a sigmoid, which manipulated our data to be on a scale from 0 to 1, and one was a rectify linear unit function, which is a piecewise linear function that either outputs 0 or the actual input value itself, depending on the positivity or negativity of the input value. And here we have a little bit more about the fit of our model. Note that our mean errors were always below $20,000 and our R-squared value was always above 0.9 and our lowest was 0.94. Here we have a visual of how close our predictions were to our data.
So having had success with a neural network when modeling the banker offer, we decided to implement a neural network to model a player's decision, whether to take the deal or not in a given round. So here we see 3 different versions of the neural net with different train test splits. In the middle, we see an 80-20, which seemed to perform consistently high. So that was probably the best of these 3. However, we eventually decided to go with a logistic regression. So this logistic regression is a model trained on the data set from POST, and it takes in around 32 variables. It outputs a probability of the player taking the deal. And if that probability of taking a deal is over 50%, we then say the player takes the deal. In the lower left, you can see what's called a confusion matrix, which models or which details what the actual raw data had deal or no deal, and what the predicted was. And the diagonal starting from the top left to the bottom right is the correct numbers, and the other diagonal is the incorrect numbers. So we can see there are a higher proportion of correct numbers. So this model predicted the player's decision with a 92.7% accuracy, and it was used to generate the decisions for the simulated players. So having a complete simulation, we could then attempt to fit a utility function to both the raw data and the simulation data. Our first attempt at a utility function was an expo power function found in a paper by Blavatsky, as you can see here. It's pretty complex, but the W is the input. The alpha parameter controls the absolute risk aversion, which we use a value from Blavatsky, which worked well. And the beta parameter controls the relative risk aversion, which is scaled by the input. And it's found experimentally because the value we found in Blavatsky didn't work well for us. So what do we input into these utility functions? Well, in each round, a contestant has a choice between 2 different distinct outcomes, taking the deal or not. So we need to model or input a utility for each of these cases. So our first attempt at the utility for taking the deal was simply plugging in the value that the player would walk away with. In this case, it would be the bank offer. This did work pretty well, but we ended up tweaking it and improving the accuracy later. Our first attempt at the utility for selecting no deal was basically to input the average predicted bank offer. We did this by running through all potential states of the next round, passing that through our banker neural net, and then averaging those values. It was very computationally difficult. All right, so after trying a multitude of configurations, we settled on the following. The utility for a deal is the bank offer plus the scale difference between the expected value of the round and the predicted expected value of that round. What this does is it incorporates this idea that people's expectations of the future is incorporated into their utility. So if they believe they're going to get a certain amount, if that time comes and they get more than they expected, their utility will be higher than if they were disappointed. This is inspired by a path-dependent model given by Koski and Rabin. So then our utility for a no deal is the average expected utility over all possible states in the next round, plus a scaled average of the predicted bank offer. And this resulted in an accuracy of up to 92.12% on the empirical data and 86.74% on the simulation data, which is pretty good, but we still think we can do better. And especially we can account for maybe audience participation and the influence of the contestants' families, which have an input in their decisions.
All right, so creating a utility function that accurately resembles humans 90% of the time, like Dylan mentioned, is pretty decent. But can we somehow make something that will allow us to derive like an optimal strategy, perhaps even better than how humans perform? Well, I mean, the short answer is we kind of can through something called reinforcement learning. And if you're not sure what this is, it's a branch of machine learning focused on creating an intelligent agent. So think of it as some sort of AI. This attempts to play the game optimally. So reinforced learning is most commonly modeled by what is called a Markov decision process, which is visualized in front of you here. Now, I'm not going to go into a lot of detail because it does get pretty complex, but in a nutshell, our intelligent agent is based off of something called a deep Q network, or DQN for short. We decided to give him a name, and we decided to call him Jeff. Jeff's brain is actually a neural network, yet it's not as convoluted as the ones we've seen earlier in the presentation. Jeff takes in an observation as an input, which is just the current state of the game that we're in. His neural net then predicts what are called Q values, which are just simply estimates of how good it is to take a certain action, whether it be deal or no deal at that point in the game. Throughout, it will remember actions that outputted higher rewards and stay away from actions that outputted negative rewards. This is all based off of some policy called pi, which is just a map that assigns probability of actions given the Q values. So for example, Jeff here uses an epsilon greedy policy, where epsilon is just this constant between 0 and 1. By default, we might choose a value of like 0.1, so 10%. So if we look at the definition for what action to choose given the state, with probability 1 minus epsilon, this is essentially saying that we exploit the best option with the max Q value. Now in the second part of the definition, with probability epsilon, we just choose a random action. So we just flip a coin and choose deal or no deal with no real rationality behind it. And this creates a stochastic element and makes it a lot less deterministic, which helps it train and just allows the agent to explore the environment more freely and learn from more mistakes. So we trained Jeff by playing 2,000 games of deal or no deal. So how did he actually do? So one thing I've learned from reinforcement learning is that it's actually very difficult to implement, especially in your own custom environment in a game like this, where you don't have control over what values or in what case. Jeff tends to end the game pretty early on, going with safe offers without maximizing winnings in comparison to human players. On the other hand, this agent occasionally prioritizes actually playing through all 9 rounds because of times it does remember saying constantly no deal and walking away with a big case, like the $1 million, for example. And thus, this creates a pretty sporadic distribution of the rounds that he ends on, as you'll see later. In attempts to improve the model, we can use a discount factor called gamma, which simply weights expected rewards in the distant future less than those in the immediate future. In our instance, we choose 0.95 because we thought it was a good metric. One thing to improve the performance of the agent is also to just give it more specific instructions, like having it take deals that are higher than the average expected value of the board, which is about $130,000. So in conclusion, if we have it play the same exact games as the simulated data, well, we can see he's not all that good, at least not yet. Considering all of these elements, it takes a lot of computational power and time to train and modify certain parameters. So the best version we have of Jeff currently goes home with more money than simulated contestants only 42% of the time. So comparing all these models, we can see if we can derive an optimal time to stop playing the game. So note in these following histograms, we actually denote round 10, stop round 10, as instances where the player doesn't take a deal and goes home with the value in their case. Empirically, past contestants actually never take the deal earlier than the 5th round. And then it also looks like most take the deal around 7 or 8 rounds of play. This distribution holds true to the simulated data, which justifies that it actually is pretty suited to replicate human behavior. Yet, if we move on to our DQN agent, Jeff, over here, he doesn't have any family or pressure from the audience to motivate him to say no deal because, well, he's an AI. So while we could tell him to not take the deal in the first 4 rounds because not enough values are off the board yet, I thought it was more interesting to just let Jeff loose, which just leads him to taking the deal a lot more early on, mainly because it remembers getting punished for choosing risky rewards.
So in the future, there's a few different directions we'd like to take this. So we can incorporate stochastic choice into our player utility model. So utility theory models assume that players will choose the option with the greatest utility, but because humans aren't perfectly rational calculating machines, sometimes they end up taking options with lower utilities. This is defined as a treble. So by nesting our utility function in a model of stochastic choice, we can incorporate this behavior into our model and possibly improve the accuracy of our predictions. And as Michael was saying, we can also modify or improve the policy and reward system of the DQN agent to better maximize winning strategies. And hopefully, as we do that, we can see the stop round get closer to the empirical data. So here are our sources. And thank you for coming. Do we have any questions?
Thank you, everybody. Round of applause for the group, please. Questions or comments for the group? Feel free to use the chat feature, or you can raise your hand if you have any questions.
You're getting lots of compliments. Great work. Great job, guys. Very interesting. Thank you. We do have a question. Were you fans of the show before this project? Are you fans of the show now?
Well, I can say personally that I had maybe only seen like 3 episodes before this project, and I've still only seen 3 episodes of the show. So I guess the answer is I'm not particularly a fan now.
Funny enough, I'd actually never watched the game show before we started this project, and I am kind of fascinated with it now. So I guess it got really overcomplicated and a lot more interesting.
I'm in the same boat as Austin. I'd never seen it before, but now I think it's pretty cool.
Yeah, and then similar to Dylan, as a kid, I definitely watched the show. Not too often, but like I've seen it enough. But I didn't really realize how kind of complex modeling this game show was until we started this project. So overall, I'm definitely a much bigger fan of the show now than I was however many years ago when I last saw it.
Speaking about the complexity of the game, Rachel is asking if this project impacted your views on psychology or human decision making.
Well, so for me, we kind of went into this kind of just thinking in terms of probabilities at first. And it definitely was kind of a slap in the face just how hard it is to model human decision behavior. I mean, it's one of the fundamental kind of ideas in economics, that people are perfectly rational beings, people make perfectly rational calculations, and then you start to realize as you try to model that that's not even close. So it was definitely very complicated.
Yeah, it definitely did impact my views on human decision making. One of the main papers that we based our project off of, which is by Post et al., had data that suggested both people who were losing in the round, losing in the game show so far and winning in the game show, they both tended to be more risk seeking. So they increased in their risk-seeking behavior as the game progressed, which is very interesting to me because like both losers and winners had the similar behavior and wanted to seek more risk. So that was an kind of a interesting psychological perspective. Yeah.
Thank you all for your questions and answers. All right, so here's our second group, focusing on polyaminos. And the group members here are Luke, William, Naftali, and Johnny. We can start whenever you're ready.
So good morning or good afternoon, folks, depending where you are. Today we're going to be talking about counting polyaminos on finite surfaces. We'll define what polyaminos are in just a minute. And for the purposes of this talk, finite surfaces means basically any surface that's not the infinite plane. So this talk will be divided into 5 parts. First, we will introduce all the definitions and concepts that we'll be discussing. Next, Luke will talk about his methods for manually enumerating polyaminos on various surfaces. But to complement his work, William will be talking about his Python algorithm for enumerating polyaminos on the plane and torus. Next, Johnny will discuss his own algorithm using transition matrices to enumerate polyaminos. And finally, I will discuss enumeration of a particular class of polyaminos that I found interesting.
Now, you may be asking yourself, what exactly is a polyomino? Well, if the word domino comes to mind, you're already familiar with an explicit example of a polyomino of size 2. We define polyominoes as objects comprised of k unit squares connected by their edges. One general question we seek to answer is, how many polyominoes of size k exist on various surfaces? When enumerating these polyominoes, we consider the distinctions of fixed and free polyominoes. Fixed polyominoes are equivalent to each other if and only if they can be translated to each other. In other words, the 19 polyominoes at the bottom of the screen are all unique despite some of them looking similar. Free polyominoes, on the other hand, are equivalent to each other if and only if they can be rotated, reflected, or translated to each other. In other words, the polyominoes within the 5 boxes would all be enumerated as a single polyomino respectively.
So our variation on the problem is counting the number of polyominoes on finite surfaces and how this affects how many there are. And specifically, we're looking at the fixed polyominoes where only translations are allowed. We're looking at the finite grid, the torus, the cylinder, Mobius strip, Klein bottle, and projective plane.
So the surfaces we will be considering can all be deconstructed or dissected into a finite grid, where the edges are connected as shown by the arrows. In order to count the polyominoes on these surfaces, we can then consider the polyominoes on the grid and then determine how each polyomino translates in accordance to each surface. To start, I decided to enumerate all the possible polyominoes on the finite grid, ranging from 1 by 1 to 3 by 3. This allowed me to get a base for what polyominoes would be possible on other surfaces. As you can see, my hand-drawn examples are sorted by their k values and grid sizes, with the red boxes notating which polyominoes are translations of each other. Each box will only count as a singular polyomino. I then repeated the same process for the torus, which has the added possibility for cells or translations or individual squares to be connected over opposite edges, allowing for more possible translations. If you look closely, you might be able to see that most torus polyominoes on the 3 by 3 grid have 9 possible translations relating to its symmetry. And most polyominoes are translationally equivalent to a polyomino previously enumerated on the finite grid. So even though there are more polyominoes drawn on the previous slide, we end up with a lower count on the torus than on the finite grid. Why is this? Well, if you look at this animation, you can see how this single polyomino can be represented by different dissections. Here we have all the translations listed out that you just saw animated. And as you can see, these polyominoes on the finite grid cannot translate, as moving over an edge is unacceptable on that surface. However, from the animation, we know that these all represent the same singular polyomino on the torus. And as I mentioned earlier, many of the polyominoes on the torus were just translations of a polyomino on the finite grid. I'm calling these dissectable polyominoes, since their surfaces can be dissected in such a way that the polyominoes will still be valid. There were, however, polyominoes on the torus such that none of their translations are valid on the finite grid, which I'm calling undissectable polyominoes. Here, for example, are all the translations of this shape, which I've named an empty diagonal polyomino, which is valid on the torus, but none of their translations are considered polyominoes on the finite grid. It presents an interesting discovery that there are some polyominoes that can be constructed on a torus, but not on a 2-dimensional grid. And we actually found that for any torus of size 3 by 3 or greater, that the empty diagonal polyominoes are all undissectable. So the Mobius strip offers an interesting twist into our process, pun intended. There are additional conditions that must be met in order for certain translations to be possible on the surface. For certain translations to be possible. On this surface, any translation horizontal to the edge maintains the polyomino structure. However, for a translation perpendicular to that edge on the 3 by 3 Mobius strip, the polyomino must have a column of empty cells also perpendicular to that edge. To show why this condition must be met for this kind of translation, take a look at this example of a size 3 center row polyomino on a 3 by 3 Mobius strip. As shown in the 3-dimensional graph, this polyomino is completely connected. Whereas if we were to translate the row up, then as you can see, the connection is broken, making this a fundamentally different polyomino in 3-dimensional space. We can then begin to compare the amount of possible polyominoes for different surfaces on different dimensions. But by hand enumeration has its limits. So to look at even higher dimensions, we must rely on computer enumeration.
To enumerate polyominoes on other surfaces, I modified an algorithm developed by Redelmeier. I will first discuss the principles of this algorithm on the infinite plane, and then touch on some changes made for the torus. One way to enumerate polyominoes and ensure that they are connected is to grow them from a starting cell. For example, starting with the red cell, we can grow it into the polyomino as shown. However, one issue with this process is that it generates duplicates. Here, we see that there are 8 ways to generate the same polyomino as before. To remove these duplicates and obtain an accurate count, we will impose two conditions. First, we will choose a location for the starting cell within the polyomino. Choosing to place it to the left in the upper row leaves us with the following tree. For our second condition, consider what would happen if we began our process not with a single cell, but with a domino. Beginning with this one, our process would generate all polyominoes containing the red cell and the orange cell to its right. To ensure that the polyominoes generated from the next domino are different from those before, we can disallow any growth to the right of the red cell, since we just counted all of those. Implementing this, we see that there is only one remaining way to generate our foramino. Applying these principles to every level of the tree, we can generate all of the foraminos. Notice that the red cell is always to the left in the upper row, and that once the cell has been added to a polyomino, it cannot be added to any subsequent polyominoes within that branch. For example, after the yellow cell is added to polyomino 3, it cannot be added to polyominoes 8 through 14. On the torus, a different condition will be needed to specify the location of the starting cell. Although in 2D it appears that there is an upper row, in 3D it becomes clear that there is not. Let's look at a smaller example on the 4x4 torus. If we let filled cells be 1 and empty cells be 0, we can obtain a binary number by reading the cells along the direction of the red arrow. We can identify a particular dissection of the torus by choosing the one with the highest binary number, which in this case is the following. Once we have done that, we now have an upper row and can place our starting cell accordingly. After implementing this algorithm, we were able to count all the polyominoes on the 2x2 through 5x5 tori, as well as up to the 19 ominoes on the 6x6 torus.
As an alternative counting method to the ones already discussed, we can use transition matrices to enumerate them for us. This method requires you to start with a grid column of a given size, which contains at least one filled cell. The polyomino will grow from the starting column by appending other columns, which also contain at least one filled cell, to the right of it. Our initial transition matrix will consist of binary entries in reference to whether a certain column configuration may be placed after a previous column configuration. Let's take a look at a relatively easy example with columns of size 2. When considering a 2x2 grid, there exists only 3 possible locations for such filled cells. The B1 configuration will have the top cell filled, B2 will have the bottom cell filled, and B3 will trivially have all cells filled. And for the purposes of this presentation, we will not consider empty columns. And again, adding one of these columns to the right of an existing column will result in either possible or not possible. Now let's observe the action of appending the 3 different column configurations to a B1 configuration. And we observe appending a B1 to a B1 preserves a connection, so we denote this by 1. Appending a B2 to a B1 does not preserve a connection, so we denote this by 0. And trivially, appending a B3 to a B1, it preserves a connection, so we denote this by 1 as well. Extending the previous example to other possible starting columns will result in the following transition matrix, with entries that describe the total number of polynomials when starting with one of the top column configurations and ending with one of the left side configurations, for, in this case, a 2x2 grid. Raising this particular matrix to the q-1 power will allow us to count the total number of possible configurations for a 2x2 grid. We can observe that the complexities will grow as we consider larger column sizes. In this case, for a column of size 3, we have 7 possible configurations as opposed to only 3 previously. Our previous examples only take into account a finite grid and not our desired torus. We can remedy this by manipulating our transition matrix enumeration method by creating a mask matrix which, through some hand waving, will alter our transition matrix such that previously illegal moves now be legal in the case of a torus.
So much like Luke, who focused on undissectable polyominoes, I've been focusing on polyominoes of a particular type, namely serpents. So I'll start with the definition. A serpent polyomino is a polyomino that basically, if you start at one cell of the polyomino, you can walk to every other cell on the polyomino, hitting its each cell exactly once. So in the examples below, if you start at the tail of any of the arrows and you follow the path of the arrow to the arrow head, you will see that all of these are in fact serpents. In fact, because of the wrapping around properties that a torus has, that each row and column wraps around on itself, on a 3x3 torus, every single polyomino is a serpent, including these two, which don't necessarily look like it. So I'll give you a moment to look at the polyominoes and see if you see any paths before we move on to the next slide. Okay, next slide, please. So if you look at the polyomino on the left, for example, you look at the lower arrow. You start at the base of that arrow, go down off the bottom of the torus, and then around the top, and continue on the top arrow. You'll see that you, in fact, hit every single cell exactly once. So this is a serpent. So we conjecture that there are, in fact, far more non-serpents than serpents, but it would be infeasible to count all non-serpents, so we decided to limit ourselves to a particular class. So we define a family of functions S sub R. Now, the way we do this is we first start with a backbone like the L shape that you see before you. That has two straight line segments joined by a corner piece. The R in S sub R refers to the number of straight line segments of this backbone. So here we would have S sub 2. S sub 2 is a function that takes in the variable K, which is the area of those segments. And then it outputs the number of non-serpents we obtain by appending a single cell to various points on that backbone. So here are some 3 examples below. We've computed explicit values for S sub R K for R up to 4. As you can see, these each give us a polynomial in K of degree R. In fact, we have proved theoretically that S sub RK will always give you a polynomial of degree R in K, and that the corresponding function, which gives you the number of serpents obtained from the same sort of configuration, gives you a polynomial of degree R minus 1. Thus, it confirms our conjecture, at least in this specific case, that the number of non-serpents will always be greater than the number of serpents. So there are some practical applications of polyominoes to the natural sciences, which, you can look into more later.
Lastly, we have some further investigations we'd like to consider, such as modifying our algorithms, enumerating toroidal non-serpents, further extending our transition matrix method, and cementing the conditions for undissectable polyominoes of an n by n torus. Thank you for joining us on our journey through polyominoes. Are there any questions?
Just like the previous group, if you have any questions or comments, feel free to use the chat box, or if you have a working mic, you can unmute yourself and ask the questions yourselves.
Do you want to introduce the question?
Yeah, so Dylan asked, is there any class of polyominoes you found particularly interesting, but you didn't have time to study?
I mean,
So,
yeah,
go ahead.
Totally. Okay, I guess I'll answer first. Mainly, we were looking at fixed polyominoes. So we were considering rotations and reflections to be different from each other. And I'd be interested in working more on counting free polyominoes where those are allowed. But of course, that can become more complex because you have to think about, for every polyomino, how many different symmetries it has, and you have to get into like group theory and algebra and stuff like that.
Naftali, do you want to add on to that question?
No, I'll take the next question if that's all right.
Okay, yeah. Next question is that the surface only applies to 2 and 3 dimensions, correct?
So we did not consider higher dimensional surfaces. It just never occurred to us. William, if you want to add something to that, go ahead.
Yeah, to be clear, all of our polyominoes, once we dissect it into a 2-dimensional grid, they all are in 2 dimensions. So, there is such a thing as a three-dimensional polyomino where you consider cubes rather than squares, but ultimately our polyominoes are more like variations of two-dimensional ones. It so happens that some of the surfaces we're working on can only be embedded in 3D space, or for the Klein bottle, even 4D space. But ultimately, the polyominoes behave more like two-dimensional ones.
I mean, we would expect that, higher dimensional analogs would function similarly, but we do not go into them specifically.
And also, to be clear, when we were talking about the dimension of surfaces, we're talking about the grid size itself, not, the spatial dimensions.
Got it. Thank you. I do have a question. So towards the end, you mentioned some applications to other sciences like chemistry. Can you maybe explain a little bit more along those lines?
Okay, so one of the applications I mentioned was benzene hydrocarbons. So this is a particular type of chemical that apparently you can enumerate the number of possible ways that this chemical can be formed using analogs of polyominoes called hexaominoes, where you replace the squares with hexagons. I don't know exactly the details of how that works, but I do have a paper on it that I can share with anyone who's interested.
More questions for our speakers?
We do have a lot of compliments in the chat. Everything from awesome presentation to interesting area. Great presentation, fantastic presentation. Excellent graphics, they help so much in the understanding. Loved the backgrounds. So overall, great job.
Is it hard to do your Beamer file, to work on you guys spend a lot of time working on your Beamer file?
Yeah, I mean, in some sense, doing it in Beamer helped because, we could easily edit our graphics when we had to make a change, especially for like all the tree structures I was making. But it took quite a while to figure out how to actually code that.
And then with each grid polyomino that we made, we had to make an individual grid and then make code each cell that was filled. So our code on the Beamer file got really long.
For sure. And your hard work didn't go unnoticed. I mean, it's awesome, the results. All right, the next group can maybe share their screen right now. Again, a round of applause for group 2, please. Okay, the next group will be talking about hormone modeling. The group members are Lexi, Emily, Rachel, and Vanessa. Whenever you guys are ready, take it away.
Okay, so hello everyone. Today we'll be talking about mathematical modeling with polycystic ovarian syndrome.
I'm Lexi.
I'm Emily.
I'm Rachel.
And I'm Vanessa. So just to go over what we'll be talking about today, we're going to go over our problem, and then we're going to go over the 3 models that we ended using, and then how we parameterized our 3rd model, and then finally our conclusions. So our goal with this project was to mathematically model a menstrual cycle specific to people who have polycystic ovarian syndrome in order to better understand the hormones that are involved in PCOS. In order to do this, we recreated existing models, and then we evaluated and verified those models. And then after doing so, we decided to start modifying the models in order to better understand polycystic ovarian syndrome.
So starting off with just a little bit of biology background, the menstrual cycle has 2 phases, the first of which is the follicular phase. Within the ovaries, there are follicles, which are fluid-filled sacs, each containing 1 immature egg. At the start of the cycle, multiple of these follicles will begin to develop as stimulated by the hormone FSH, which is released from the pituitary in our brain. And these follicles begin to grow and they will release estrogen. And this estrogen has a negative feedback loop on FSH levels. However, only one of these follicles will become the pre-ovulatory or dominant follicle, and the rest of them will die off through the process of atresia. And at around day 14, there is a large surge of LH and also a smaller surge of FSH hormones, and that is when ovulation will occur.
So after that surge of LH and FSH causes the follicle to rupture and release the egg, we're left with the mass of the follicle, and that'll transition into the corpus luteum due to the luteinizing hormone LH. And the corpus luteum produces estrogen, progesterone, and inhibin, all of which helps regulate the cycle. So the corpus luteum will decay over the next 14 days. And if there's no fertilized egg, the cycle will restart. But if there is one, progesterone and estrogen will both help ready the body for pregnancy. So PCOS, or polycystic ovary syndrome, is a hormonal reproductive disorder that affects about 10% of females globally. So it's typically characterized by high testosterone, which is an androgen, high LH and insulin, as well as lower levels of FSH and progesterone. So the scientific literature isn't super clear yet on what causes PCOS. We know that there's a lot of contributing factors, but as far as pinpointing a specific or main cause, it's still unclear. We do know that low FSH levels lead to the follicles not maturing enough to develop into that dominant follicle and release an egg. Instead, they become cysts. So these cysts keep producing estrogen and they contribute to a hormonal imbalance. That imbalance causes many side effects like infertility, weight gain, insulin resistance, depression, and other health issues.
So our first step in this process was creating a model for normal ovulation, and we were able to find a system of differential equations through a paper written by Chen and Ward. This had a system of 3 differential equations, the first of which followed the follicular phase and covers the rate of growth of the dominant follicle until ovulation. That second equation covers the scar tissue as the follicle ruptures. And then that third equation follows the luteal phase and the rate of decay of the corpus luteum.
So after recreating this model, we noticed that our simulations did not match the models that were shown in Chen and Ward. So in order to investigate this further, we decided to compare our model to the data that Chen and Ward referenced by McLaughlin et al. So on the left, you can see our 2 simulations where the dots represent the raw data from McLaughlin and the lines are our simulation. And so we focused on LH and FSH in part due to the amount of data that's available, but also because LH and FSH have such important roles in the menstrual cycle. So you can see there's a misalignment between the raw data and our simulation. So moving forward, we began to look at other hormones that might impact the system, like androgen, in order to address this misalignment.
So we really wanted to model in androgen or testosterone, and we found a model that did that. So the Hendricks-Hughes cell grade model is a system of 16 differential equations. So starting at the left middle at PRA1, moving through the first 6 terms there, we see the first 6 phases of the follicle, from starting out to the ovulatory follicle, which will then release the egg at day 14. The next 2 equations model the transition to the corpus luteum, and the last 4, the lute 1 through lute 4, are the corpus luteum in different phases of decay. And this model also includes 5 auxiliary equations for estrogen, progesterone, testosterone, and inhibins A and B, all of which are very important to keep the cycle running.
So we were incredibly excited about this model, but we had also been interested in adding birth control, which is something that the Wright et al. Model lacked. We were specifically interested in including birth control because it is often used as a treatment for those with PCOS, as it helps regulate their cycle. And we actually were able to find a paper written by Wright et al., and they used parameters for progesterone and estrogen hormone control. This had a system of 13 differential equations, and we noticed that there was a lot of overlap and similarities between the Wright model and the Hendricks model, and we wanted to combine the 2.
So when we wanted to combine them, we had to incorporate another differential equation, which brought us to 17 differential equations, and changed existing differential equations, added another auxiliary equation, which brought us to 6 auxiliary equations, and incorporated new parameters to existing auxiliary equations. And then on the next slide, you'll be able to see what changes we made in the blue. are from the right model, and then everything in black was from the Hendrix model. So RCF was the recruited follicle that changed the denominator, which was added from the right paper, the growing follicle, which was completely in the right paper, which we decided to add, and in doing so, that changed the dominant follicle. And then in the next slide, the auxiliary equations, PAPP was added, which was where everywhere the right model used P4, we replaced with PAPP because that's what the right model did. And then on top of that, we added parameters for E2 and P4, especially E-dose and P-dose, because we wanted to add birth control in our model.
So these are the resulting graphs of this combined model. And as you can probably see, our lines are lining up much better with the data than the original Chen and Ward paper. There are still some inconsistencies, and the main thing that we wanted to focus on was LH and FSH levels. As you can see, the peaks are going beyond the data points, and we really wanted to change that through parameterization. So we ended up changing a total of 5 parameters. The first 3, mu, 0, LH, mu, and Ki, FSHA, all contributed to decreasing those LH and FSH levels. But because this is a system of differential equations, changing those will also affect the rest of the graphs. And because of this, we needed to increase estrogen and progesterone levels. And through this, we were able to do this through changing the parameters E3 and P2. So this is our final graph for regular ovulation, and we are pretty happy with it. There's a couple inconsistencies. If you look at the LH graph, there is a surge right in the first 2 days, and this doesn't really follow biology, and we aren't entirely sure why this surge appeared in our model. So that's something we're interested in looking into maybe later on. And we also were unable to completely match the data of testosterone, but we also believe that this is still a good representation because testosterone gets converted into estrogen. And so in order for that estrogen surge to happen between day 10 and 15, there also needs to be that surge of testosterone.
So now that we have a working regular ovulation model, we wanted to expand and address polycystic ovarian syndrome. So first, we began to adjust our regular model in order to model ovulation in people who have polycystic ovarian syndrome. However, we must keep in mind that the biological data of hormone profiles for PCOS is limited. So we were only able to use LH and E2. And then after creating a working polycystic ovarian syndrome model, we want to look at the impact of hormone control on that system.
So like Vanessa said, we began with a source that said LH levels and FSH levels in a normal cycle are usually close. So then in PCOS, LH values are usually 2 or 3 times that of FSH values. So what we did was take the FSH values from our normal data and then multiplied it by 2.5. In the red dots is that data. And then I parameterized the LH and 4 parameters changed to match to get the PCOS model for LH. And then after obtaining parameterizing LH, we decided to parameterize E2. And because we had a standard deviation from a different source that gave the levels for PCOS. In doing so, only one parameter needed to be changed for E2 to get it in the below 2 red lines. And then after parameterizing LH and E2, we were able to see what effects on the other hormones this model had. And this decreased like everything pretty much, other than it decreased testosterone as well. And this aligns with what biology says for PCOS modeling. The only thing is that testosterone is usually higher in PCOS patients. And here it aligns with our data better. But like we said before, it was an inconsistent normal model. With having this PCOS model, we wanted to have it to be able to make it normal with birth control.
So adjusting the parameters established by Wright et al., we first started with a high dose of progesterone. So progesterone and estrogen both are used as birth control because they both help regulate cycles. And PCOS patients typically have lower progesterone than normal. So we were hoping that this would achieve somewhat of a regular cycle. But we can see on the left of the graph, there's still a really high spike of LH, which doesn't fit the normal biological understanding of a regular cycle, as well as there lacks any sort of spike of LH and FSH around day 14 or 15. So we weren't really happy with this. So moving on, we tried to implement a high dose of estrogen, and this made our model look really good. We had a spike of FSH and LH both at the regular time, and this made our model look closest to a normal cycle with those PCOS parameters. We also wanted to try a combined dosage of low amounts of progesterone and estrogen. So this did align closely to data points we had. FSH didn't peak as much as we would expect it to, but overall the model looks okay. So while we were happier with the E dose of how it made our graph look, the combined low dose may be important to model because of the clinical significance. So giving people in the real world a high dose of estrogen can come with a lot of side effects, whereas administering a combined low dosage of estrogen and progesterone have fewer side effects. So it's also important to look at.
So to conclude, we believe that current models for human ovulation can still be built upon. Throughout this presentation, we've shown that, and we've begun the work on being able to model and explain PCOS. And so we believe as the biology world discovers more about ovulation and PCOS specifically, that the models will begin to reflect that. And if we were to continue this research, we would like to obtain more PCOS data, whether that's partnering with someone who has access to that data or finding better data sources. And we would also like to include other relevant hormones within the system. And then finally, we would like to construct a better equation for testosterone in order to fix that misalignment that there was. Lastly, we would like to acknowledge a few people. We would like to acknowledge our research advisor, Dr. Brandy Wiegers, for helping us throughout this whole process. And we would like to thank Dr. April Binder, who is part of the biology faculty at Central Washington University, for allowing us to pick her brain on PCOS. And here are our references. And thank you for listening to this presentation. Are there any questions?
Applause for this group. As usual, questions can be asked using the chat feature, or if you want to unmute yourself, you can also ask the questions yourselves.
I have a question for you guys. So this being such a biology heavy topic, and I mean, I don't know how much background you guys have in biology. Was that a really difficult part to try to get yourself educated to the level where you could actually start doing full research?
To be honest, I have zero background in biology. So for me, it was probably I feel like the most challenging out of all of us, because I kept on asking them questions and we were all a little bit unsure. So it was probably the first whole week of our research was just understanding normal menstruation, and then figuring out what PCOS is was a really big part of our research experience.
Yeah, I would agree with that. It was probably about a week's worth of work of getting all of that information. I think one thing that was also helpful was having that starting model only with 3 equations kind of placed in the different phases rather than all of the complexities kind of helped us get that basis idea. And so when we found the Hendricks et al. Paper, which was more specific, we kind of had a better understanding of biology as we continued to build it up throughout the weeks, and it was easier to kind of implement it through there.
Great, and I think that also answers Dr. Uperte's question to how you learn biology. I have a question about specifically slides 14 and 17, where you change the parameter values. How do you go about doing that? Is this experimentally determined, or is this based on some scientific procedures?
So it was kind of like a team effort, I would say, with each of us looking at a different part of our graph. So one of us would do like LH, one of us would do E2, one of us would do testosterone, and then we would take one parameter, change it, figure out what it does to all of the graphs, and then see like increasing or decreasing, and then kind of making this like document with what each parameter does. And then we took all of that knowledge on the different parameters to get like combine them and then see what happens with the other ones. So it was a very long process to try and fit the data that we had.
And ultimately, instead of trying to get the parameters to match like data on like hormone levels, we were trying to get the shape of our simulations to match the plotted data often.
Thank you. Any more questions or comments for this group?
We see in the chat, it says, thank you for the wonderful presentation, very relevant topic, great job, amazing job. Awesome presentation, very informative. So very well organized. So can we thank our speakers one more time? I want to take a moment before we take off and just thank especially all of the family members that joined us today. I know that our students appreciated so much of the support that they received from you as family members and being able to take and do this summer project. And I also want to take a moment and thank our other advisors. So Dr. Loke and Dr. Montgomery have really helped guide the students through this process. And I want to take a moment and make sure to recognize them and their work, along with the 12 students that have done this project. So can we just do one more round of applause to say thank you to everyone? And just thank you for joining us today. I hope you have a wonderful day, and we look forward to getting to continue to present this work.